Subscribe to the channel so you don't miss out on any of these videos. The space between galaxies, the void that seems empty and endless, holds one of the greatest mysteries of our universe. It's a realm that's easy to overlook because it appears so still, so desolate. But hidden in that vast expanse lies something remarkable: the intergalactic medium, IGM. This invisible sea of gas and plasma stretches across the cosmos, filling the space between galaxies and weaving through the threads of our universe. Despite its elusive nature, the IGM plays an essential role in the structure, evolution, and very fabric of the cosmos. And yet, most people have never heard of it. Why? Because it's nearly impossible to see and even harder to fully understand. Here's the intriguing part. Scientists believe this seemingly invisible matter might be the answer to one of the biggest puzzles in astrophysics. You've probably heard of dark matter and how most of the universe's mass is hidden from us, defying direct observation. But the intergalactic medium could hold significant portions of this missing mass. It's not quite dark matter, but it's not what we'd call ordinary matter either. It's something in between, scattered so thinly that it defies easy detection. This revelation isn't just fascinating, it's transformative. If the intergalactic medium really does house this missing mass, it could reshape how we see the universe and our place in it. But what exactly is the intergalactic medium? Imagine a spider's web stretching across the universe. The galaxies are like the bright, beaded nodes, but the faint filaments of gas connecting them are what make up the IGM. These filaments are vast but almost unimaginably diffuse, with particles spaced so far apart that you could travel for light years and barely encounter a single atom. Despite its sparseness, the IGM is a cosmic bridge, tying together galaxies, star systems, and even clusters of galaxies into a unified structure. Here's the kicker: the IGM wasn't always so spread out. Billions of years ago, in the early universe, this gas was much denser, concentrated into pockets where stars and galaxies began to form. The IGM is the leftover material from this process, the scattered remnants of the primordial soup from which everything we know emerged. It's like a time capsule from the universe's infancy, preserving clues about its origins, composition, and eventual fate. So, how do scientists study something so faint and diffuse? They use quasars, some of the brightest objects in the universe, as cosmic flashlights. When light from a quasar travels through the IGM, it interacts with the gas, leaving behind telltale signatures in its spectrum. These absorption lines reveal the chemical composition, density, and temperature of the intergalactic medium. Through these subtle imprints, astronomers can map out the IGM and uncover its secrets. One of the most exciting discoveries about the IGM is its connection to the cosmic web. This intricate network of filaments is the backbone of the universe, a vast structure shaped by gravity over billions of years. The IGM flows along these filaments, feeding galaxies with fresh material and enabling star formation. Without the IGM, galaxies would starve, and the universe as we know it would cease to exist. But the IGM isn't just a passive player in the cosmic drama. It's an active participant, influenced by powerful events like supernovae, black hole activity, and galactic winds. When massive stars explode, they eject material at incredible speeds, enriching the IGM with heavy elements like carbon and oxygen. These elements, in turn, become the building blocks for new stars and planets. It's a cosmic recycling program on the grandest scale imaginable. Even more intriguing is the role of the IGM in galaxy evolution. Galaxies are not isolated islands. They're deeply connected to their surroundings, drawing in gas from the IGM to fuel star formation. At the same time, galaxies eject material back into the IGM through powerful winds driven by supermassive black holes and starbursts. This constant exchange of matter and energy shapes the galaxies and the intergalactic medium, creating a dynamic interplay that influences the entire universe. And yet, the IGM remains one of the least understood components of the cosmos. Detecting it requires highly sensitive instruments and cutting-edge technology, and even then, much of it remains elusive. Recent advancements, like the Cosmic Origin Spectrograph on the Hubble Space Telescope, have provided unprecedented insights into the IGM, but there's still so much we don't know. For example, How does the IgM evolve over time? What role does it play in the distribution of dark matter? And how does it interact with the mysterious forces driving the universe's expansion? One of the most mind-boggling aspects of the IgM is its relationship with dark energy. Dark energy is the enigmatic force responsible for the accelerating expansion of the universe, and the IgM might hold crucial clues about how it works. By studying the IgM, scientists hope to understand the balance of forces shaping the cosmos and perhaps even unlock the secrets of dark energy itself. What's truly humbling about the IgM is its sheer scale. While galaxies like our Milky Way might feel enormous to us, they're just tiny specks in the vast ocean of the intergalactic medium. The IgM is the stage on which the entire cosmic story unfolds, and without it, there would be no galaxies, no stars, no life. It's a reminder that the most important things in the universe aren't always the most visible. And yet, the IgM raises profound questions about our understanding of the cosmos. If so much of the universe's mass is hidden in this diffuse medium, what else might we be missing? Could there be other forms of matter or energy lurking in the shadows, waiting to be discovered? The IgM is a testament to the fact that the universe is far stranger and more complex than we ever imagined. It challenges our assumptions and pushes the boundaries of what we think is possible. As we continue to explore the intergalactic medium, we're not just uncovering the secrets of the universe, we're redefining our place within it. The IgM is a reminder that even in the vast emptiness of space, there's beauty, complexity, and meaning. It's a hidden thread in the tapestry of the cosmos, binding everything together and illuminating the interconnectedness of all things. The intergalactic medium also has a fascinating relationship with cosmic radiation. Space is not silent. It's filled with high-energy particles zipping through the void at nearly the speed of light. These cosmic rays interact with the IgM, creating shockwaves and scattering energy across vast distances. Over billions of years, these interactions have shaped the thermal history of the universe. The IgM, though faint and cold in many regions, contains pockets of heated gas energized by such cosmic events. These interactions have a ripple effect, influencing galaxy formation, star formation, and even the chemistry of intergalactic space. But why does the IgM matter to us? Beyond its contribution to the universe's mass and structure, it provides a window into the distant past. The intergalactic medium carries the imprint of the universe's history. By studying it, scientists can trace back to the era when the first stars ignited and the first galaxies assembled. The IgM is like a fossil record, preserving evidence of processes that occurred billions of years ago. For example, the reionization era, when the first stars and galaxies ionized the neutral hydrogen gas filling the universe, left distinct marks on the IgM. Understanding this critical period helps us piece together how the cosmos transformed from a dark, featureless expanse to the vibrant, structured universe we see today. The chemical composition of the IgM is another treasure trove of information. By analyzing the light from distant quasars as it passes through the IgM, scientists have detected elements like hydrogen, helium, carbon, and oxygen. These elements tell the story of stellar evolution and nucleosynthesis, the process by which stars forge heavier elements. But the IgM also holds mysteries. For example, there are regions where metals, like oxygen and iron, appear in concentrations far higher than expected. How did these elements get there? Did they travel through galactic winds, or were they dispersed by powerful cosmic events like gamma-ray bursts? These questions highlight how much we still have to learn about the interplay between galaxies and the intergalactic environment. One of the most exciting areas of research involves mapping the cosmic web. Imagine being able to see the hidden scaffolding of the universe, the vast network of filaments connecting galaxies like pearls on a string. This structure is where the IgM resides, and it provides critical insights into the distribution of matter in the universe. Advanced computer simulations and observations are now allowing astronomers to reconstruct this cosmic web in stunning detail. These maps not only reveal the location of galaxies and clusters but also highlight the vast reservoirs of gas that feed them. The cosmic web is more than just a visual representation, it's a dynamic system. The IgM flows along these filaments, forming streams of gas that feed galaxies and fuel star formation. At the intersections of the web, where filaments converge, you find galaxy clusters, the largest structures in the universe held together by gravity. The IgM acts as a highway, transporting material between these clusters and shaping their evolution. Without this interconnected network, the universe would look very different. Interestingly, the IgM also interacts with magnetic fields on a cosmic scale. These magnetic fields are incredibly weak, but they stretch across vast distances, influencing the movement of charged particles within the IgM. How these magnetic fields formed and evolved remains one of the great unanswered questions in astrophysics. Some theories suggest they originated from the Big Bang, while others propose they were amplified by processes within galaxies. Either way, their presence within the IgM adds another layer of complexity to this already intricate system. Another intriguing aspect of the IgM is its potential connection to dark matter. While dark matter remains invisible and elusive, it is thought to play a critical role in shaping the universe's large-scale structure. The IgM traces the distribution of dark matter, following its gravitational influence to form the cosmic web. By studying the IgM, scientists can indirectly map the location and behavior of dark matter. This indirect approach has provided some of the strongest evidence for dark matter's existence, and has helped refine our understanding of its properties. But the mysteries don't end there. Recent observations have hinted at the presence of warm-hot intergalactic medium, WIM, a subset of the IgM that exists at temperatures ranging from hundreds of thousands to millions of degrees. This WIM is thought to house much of the universe's missing baryonic matter, the ordinary matter made of protons and neutrons that should account for about 5% of the universe's total mass, but hasn't been fully accounted for in galaxies or galaxy clusters. Detecting this WIM is no easy feat, as its low density and high temperature make it incredibly faint. However, advanced X-ray telescopes have begun to uncover its secrets, bringing us closer to solving the puzzle of the universe's missing mass. The IgM also plays a role in cosmic feedback mechanisms. When massive galaxies or galaxy clusters eject material, the energy released can heat the surrounding IgM, preventing it from cooling and condensing into new stars. This feedback loop regulates star formation across the universe, ensuring that galaxies don't grow uncontrollably. At the same time, this process enriches the IgM with heavy elements, creating a cycle of enrichment and redistribution that connects galaxies to the intergalactic environment. Even more fascinating is how the IgM interacts with cosmic voids, immense regions of space with almost no galaxies or matter. These voids are surrounded by the filaments of the cosmic web, where the IgM resides. Studying these voids and their interaction with the IgM can provide insights into the nature of dark energy and the universe's expansion. The stark contrast between the dense filaments and the empty voids highlights the delicate balance of forces shaping the cosmos. In essence, the intergalactic medium is a story of connection. It links galaxies, stars, and clusters into a unified whole, showing us that nothing in the universe exists in isolation. The IgM is a reminder that even in the vast emptiness of space, there is structure, purpose, and meaning. Its study challenges our perceptions, pushing us to explore the unseen and rethink our understanding of the cosmos. As we continue to probe the intergalactic medium, we're not just learning about the universe, we're uncovering the very fabric of reality. Each discovery brings us closer to answering the ultimate questions about where we come from, where we're going, and what lies beyond the stars. The intergalactic medium, IgM, is not only a bridge between galaxies but also a frontier for groundbreaking discoveries about the very origins of the universe. To truly appreciate its significance, one must dive deeper into the mechanisms that govern its behavior and the tools that scientists use to study this elusive entity. Let's start with how light serves as our cosmic messenger. When light from distant galaxies or quasars travels through the IgM, it interacts with the gas and plasma along its journey. This interaction leaves telltale absorption lines in the light spectrum, a phenomenon known as the Lyman alpha forest. These absorption lines correspond to neutral hydrogen in the IgM and appear as a dense forest of lines in the spectrum of high redshift objects. By analyzing these patterns, scientists can map the distribution of hydrogen in the IgM, revealing its density, temperature, and movement over cosmic time. The Lyman Alpha Forest provides more than just a map, it is a time machine. Light from quasars, some of the most luminous objects in the universe, has traveled for billions of years to reach us. As it passes through the IGM, it carries with it a record of the conditions that existed at various stages of the universe's evolution. By piecing together this data, researchers can reconstruct a timeline of how the IGM and the cosmic web evolved. Yet, there are still gaps in our understanding. One of the most perplexing questions is how the IGM was reionized after the so-called Dark Ages of the universe. After the Big Bang, the universe was a hot, dense plasma. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, making the universe opaque to light. This era, known as the Dark Ages, ended with the emergence of the first stars and galaxies, whose light ionized the hydrogen in the IGM, making the universe transparent again. However, the exact mechanisms and timeline of this reionization process remain an active area of research. The IGM also holds clues about the distribution of dark energy, the mysterious force driving the accelerated expansion of the universe. By studying the large-scale structure of the cosmic web and the flow of matter within the IGM, scientists can gain insights into how dark energy influences the universe's growth. The interplay between dark energy, dark matter, and the IGM is like a cosmic dance, shaping the fabric of space-time itself. Another fascinating aspect of the IGM is its role as a testing ground for fundamental physics. The extreme conditions of intergalactic space, low densities, high energies, and vast distances, allows scientists to test theories about the behavior of matter and energy under conditions that cannot be replicated on Earth. For example, the IGM may hold answers to questions about the nature of cosmic rays, the behavior of magnetic fields on galactic scales, and even the properties of neutrinos, elusive particles that pass through ordinary matter almost undetected. Despite its significance, observing the IGM is an enormous challenge. The gas and plasma are incredibly diffuse, making them difficult to detect directly. Advances in technology, however, are opening new windows into this hidden realm. Next-generation telescopes like the James Webb Space Telescope, JWST, and the European Extremely Large Telescope, ELT, are equipped to study the IGM with unprecedented sensitivity. These instruments can capture faint emissions from intergalactic gas, detect the WIM, and probe the faintest filaments of the cosmic web. Simulations also play a critical role in understanding the IGM. Using supercomputers, scientists create detailed models of how the universe evolves from the Big Bang to the present day. These simulations incorporate the physics of gravity, hydrodynamics, and radiation to recreate the formation of galaxies, clusters, and the cosmic web. By comparing these models to observational data, researchers can refine their understanding of the processes that govern the IGM. Interestingly, the IGM is not static. It evolves over time, influenced by the activity of galaxies and cosmic phenomena. Galactic winds, for instance, can eject material from galaxies into the IGM, enriching it with heavy elements. These winds are driven by intense star formation, or the energy released by supermassive black holes at the centers of galaxies. When these outflows collide with the IGM, they create shockwaves, heating the gas and spreading elements like carbon, oxygen, and iron over vast distances. This enrichment process is crucial for understanding the chemical evolution of the universe. Without the IGM serving as a reservoir and distributor of elements, the diversity of chemical compositions observed in galaxies today would not exist. The IGM essentially acts as a cosmic recycling system, ensuring that the building blocks of life, like carbon and oxygen, are dispersed throughout the cosmos. The interplay between the IGM and galaxy formation is another area of intense study. Galaxies grow by accreting gas from the IGM along the filaments of the cosmic web. This gas fuels the formation of stars and the growth of supermassive black holes. At the same time, galaxies can influence the IGM through feedback processes, creating a complex, dynamic relationship. Understanding this interplay is key to unraveling the mysteries of how galaxies form and evolve. As we continue to explore the IGM, we are confronted with profound questions about our place in the universe. The vastness and complexity of the intergalactic medium remind us that we are part of a much larger story, a story that spans billions of years and stretches across incomprehensible distances. The IGM is not just a scientific curiosity, it is a testament to the interconnectedness of all things, from the smallest particles to the largest structures in the universe. The study of the intergalactic medium is still in its infancy. Each new discovery raises more questions than it answers, pushing the boundaries of our knowledge and challenging our understanding of the cosmos. As we continue to probe this hidden realm, we may uncover secrets that not only redefine our understanding of the universe but also reveal new insights about the fundamental nature of reality itself. The exploration of the IGM is a journey into the unknown, a quest to uncover the invisible forces that shape our universe. It is a reminder that even in the vast emptiness of space, there is a richness and complexity that defy imagination. The more we learn about the IGM, the more we realize how little we truly know, and how much there is still to discover. The intergalactic medium, IGM, is a cosmic treasure chest, overflowing with mysteries that scientists are still working to unravel. Its very existence challenges our preconceived notions of what constitutes the universe's structure and dynamics. The IGM acts as a bridge, linking galaxies, while simultaneously being a player in the grander cosmic narrative, a narrative that stretches back to the birth of the cosmos itself. The more we investigate this medium, the clearer it becomes that it is not merely a passive bystander in the story of the universe but an active participant in shaping galaxies, distributing matter, and revealing the deeper truths of our origins. One of the most compelling aspects of the IGM is its ability to act as a repository of cosmic history. Unlike galaxies, which undergo turbulent processes such as star formation, supernovae explosions, and black hole activity, the IGM provides a more stable record of the conditions that existed in the early universe. This stability makes it a sort of time capsule, holding clues about the universe's infancy. The IGM's density fluctuations, for example, tell the story of how matter clumped together under the influence of gravity to form the cosmic web. This web, an intricate network of filaments connecting galaxy clusters, is the scaffolding upon which the universe is built. Within these filaments, the IGM plays a dual role. It serves as a supply line, feeding galaxies with the gas necessary for star formation, and as a battleground where the forces of gravity and cosmic expansion collide. Another fascinating aspect of the IGM is its thermal history. The temperature of the IGM has evolved over billions of years, influenced by various cosmic events. During the universe's early epochs, the IGM was predominantly cool and neutral. However, the era of reionization, when ultraviolet light from the first stars and galaxies ionized the hydrogen in the IGM, marked a dramatic turning point. This reionization heated the IGM to temperatures of tens of thousands of degrees, a state that it maintains even today in many regions. Understanding the timeline and mechanisms of this heating process is critical to piecing together the universe's history. Adding to the complexity is the presence of the warm-hot intergalactic medium, WIM. This elusive component of the IGM is thought to contain a significant portion of the universe's missing baryonic matter. Baryons are the particles, like protons and neutrons, that make up ordinary matter, as opposed to dark matter. Observations and simulations suggest that the WIM resides in the filaments of the cosmic web, existing at temperatures between 100,000 and 10 million Kelvin. Detecting the WIM is a challenging endeavor, as its diffuse nature makes it faint and difficult to observe directly. However, X-ray telescopes and other advanced instruments are beginning to shed light on this hidden reservoir of matter, bringing us closer to solving one of cosmology's greatest mysteries. What's particularly intriguing is how the IGM serves as a mediator in the cosmic ecosystem. Galaxies do not exist in isolation, they are embedded within the IGM, and the exchange of matter and energy between the two is continuous. For instance, when massive stars within galaxies explode as supernovae, they eject enriched material into the IGM. This material includes heavier elements like carbon, oxygen, and iron, which were forged in the hearts of stars. Over time, this process enriches the IGM, seeding it with the building blocks of planets, and ultimately, life itself. Conversely, the IGM also replenishes galaxies. Through a process known as cold gas accretion, galaxies draw in pristine gas from the IgM along the filaments of the cosmic web. This gas serves as the raw material for star formation, fueling the growth and evolution of galaxies. The interplay between outflows and inflows creates a dynamic feedback loop, ensuring that the IgM and galaxies are inextricably linked in their evolution. Studying the IgM also offers profound insights into dark matter, the mysterious substance that makes up about 27% of the universe's total mass energy content. While dark matter does not interact with light in the way ordinary matter does, its gravitational influence is crucial in shaping the large-scale structure of the universe. The distribution of the IgM traces the underlying dark matter framework, providing indirect evidence of its presence. By mapping the IgM, scientists can infer the distribution and behavior of dark matter, bringing us closer to understanding this enigmatic component of the cosmos. Moreover, the IgM's relationship with dark energy adds another layer of intrigue. Dark energy, which accounts for roughly 68% of the universe's mass energy content, drives the accelerated expansion of the universe. The IgM, being interwoven with the cosmic web, is directly influenced by this expansion. The stretching of space alters the density and temperature of the IgM, leaving an imprint on its structure and properties. By studying these imprints, researchers hope to uncover the nature of dark energy and its role in shaping the universe's fate. On the observational front, technological advancements are opening new avenues for exploring the IgM. Instruments like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided unprecedented views of the IgM, revealing its complexity in exquisite detail. Future missions, such as the Square Kilometer Array, SK, and the Lynx X-ray Observatory, promise to take this exploration to new heights. These tools will enable scientists to probe the faintest and most distant regions of the IgM, unveiling secrets that were previously beyond our reach. Simultaneously, advancements in computational astrophysics are revolutionizing our understanding of the IgM. High-resolution simulations of the universe's evolution allow researchers to model the behavior of the IgM with remarkable accuracy. These simulations incorporate a wide range of physical processes, from the effects of supernovae and black holes to the influence of cosmic magnetic fields. By comparing these models with observational data, scientists can refine their theories and uncover the mechanisms driving the IgM's evolution. Ultimately, the study of the IgM is about more than just understanding a particular component of the universe. It's about piecing together the grand puzzle of cosmic evolution. The IgM is a microcosm of the universe itself, embodying its complexity, interconnectedness, and vastness. It reminds us that even in the seemingly empty voids of space, there is a richness and dynamism that defy imagination. The exploration of the intergalactic medium is still in its infancy, but each discovery brings us closer to answering some of the most profound questions about our universe. What is the true nature of the cosmic web? How do galaxies and the IgM co-evolve? What role does the IgM play in the grand scheme of cosmic history? These questions, and countless others, drive the relentless pursuit of knowledge, pushing the boundaries of human understanding. The intergalactic medium, IgM, stands as a testament to the universe's complexity, embodying its interconnected and ever-changing nature. To fully grasp its significance, we must also explore the interplay between the IgM and cosmic radiation, specifically the cosmic microwave background, CMB, and extragalactic background light, EBL. These forms of radiation act as both messengers and modifiers of the IgM, revealing its properties while shaping its evolution. The cosmic microwave background is the afterglow of the Big Bang, a faint radiation that permeates the universe. It serves as a backdrop against which the IgM is observed, particularly when studying large-scale structures. As CMB photons traverse the IgM, they interact with its particles, providing clues about its temperature, density, and composition. A phenomenon known as the Sunyaev-Zeldovich effect, for instance, occurs when CMB photons scatter off high-energy electrons in the IgM. This scattering subtly shifts the photon's energies, creating detectable distortions in the CMB spectrum. By analyzing these distortions, scientists can infer the properties of the IgM and the galaxy clusters it envelopes. On the other hand, the extragalactic background light, composed of ultraviolet, visible, and infrared radiation from stars and galaxies, interacts with the IgM in ways that reveal its opacity and enrichment. High-energy photons from the EBL ionize the IgM, maintaining its largely ionized state since the epoch of reionization. The opacity of the IgM to these photons depends on its density and composition, offering a means to study its evolution over cosmic time. Understanding this interaction also sheds light on the star formation history of the universe, as the EBL serves as a record of stellar activity throughout cosmic history. The IgM is not merely a passive recipient of radiation, it actively modifies these cosmic signals. For example, the Lyman alpha forest, a series of absorption lines observed in the spectra of distant quasars, results from light passing through clouds of neutral hydrogen in the IgM. These absorption lines provide a detailed map of the IgM structure, allowing astronomers to trace the distribution of matter across vast cosmic distances. Each line in the forest represents a unique imprint of the IgM's interaction with quasar light, offering a glimpse into its density fluctuations and temperature variations. Additionally, the IgM's role in cosmic magnetism is an emerging area of study that promises to unlock new dimensions of understanding. Magnetic fields are ubiquitous in the universe, but their origins remain one of astrophysics' enduring mysteries. The IgM may hold the key to this puzzle. Observations suggest that primordial magnetic fields, generated during the early universe, were amplified by processes within the IgM. These fields, though incredibly weak, could have seeded the stronger magnetic fields observed in galaxies and clusters today. Studying the IgM's magnetic properties may therefore provide insights into the genesis and evolution of cosmic magnetism. The IgM also acts as a laboratory for studying the interplay of gravity, thermodynamics, and fluid dynamics on cosmic scales. The motion of gas within the IgM is governed by a delicate balance between gravitational forces, thermal pressure, and cosmic expansion. Shocks and turbulence within the IgM, driven by phenomena such as galaxy collisions and supernova explosions, create intricate patterns of motion and heating. These processes not only shape the IgM itself but also influence the formation and evolution of galaxies embedded within it. One particularly intriguing phenomenon is the IgM's ability to serve as a reservoir for enriched material expelled by galaxies. Supernova-driven winds and active galactic nuclei, AGN, eject vast quantities of gas into the IgM, enriching it with heavy elements like oxygen, silicon, and iron. These metals, created in the cores of stars, are critical for understanding the cycle of matter in the universe. The distribution and abundance of these elements in the IgM provide a record of star formation and galactic activity over billions of years. By studying this enrichment, scientists can reconstruct the history of galaxy evolution and the processes that shape the cosmos. The interaction between the IgM and AGN is particularly noteworthy. AGN are powered by supermassive black holes at the centers of galaxies, which release enormous amounts of energy as they accrete matter. This energy drives powerful outflows that heat and displace gas in the surrounding IgM. These outflows can suppress star formation in nearby galaxies by depriving them of the cold gas needed to form new stars. At the same time, they enrich the IgM with metals and heat, altering its properties and creating feedback loops that influence galaxy and cluster evolution. Beyond its physical properties, the IgM plays a critical role in cosmology, serving as a testing ground for fundamental theories about the universe. For instance, the IgM structure provides evidence for the Standard Model of Cosmology, which describes the universe as composed of dark energy, dark matter, and ordinary matter. Observations of the IgM are consistent with predictions from this model, supporting its validity. However, deviations from these predictions could hint at new physics beyond the Standard Model, making the IgM a potential window into uncharted territories of science. The IgM also offers opportunities to study the nature of dark matter and its interactions with ordinary matter. While dark matter does not emit, absorb, or reflect light, its gravitational effects shape the distribution of the IgM. Simulations of cosmic structure formation, which include dark matter, provide remarkable matches to observe distributions of the IgM and galaxies. Yet, unanswered questions remain. Could there be a more direct way to detect dark matter's influence on the IgM? What role does dark matter play in the thermal and chemical evolution of the IgM? These questions drive ongoing research, with the IgM serving as a critical arena for exploring the unknown. The IgM reminds us of the vastness and interconnectedness of the cosmos. Its presence connects galaxies across incomprehensible distances, forming a web of matter and energy that spans the universe. Studying the IgM is not just about understanding its specific properties. It is about uncovering the larger tapestry of cosmic evolution. It challenges us to think on scales that dwarf human experience, to consider processes that unfold over billions of years, and to seek answers to questions that lie at the very limits of human understanding. As we continue to explore the intergalactic medium, we are not merely uncovering the secrets of the universe's hidden matter. We are engaging with the profound mystery of existence itself. The IgM, with its ethereal presence and cosmic significance, serves as a reminder that even in the vast emptiness of space, there is beauty, complexity, and an unending source of wonder. The intergalactic medium, IgM, is more than just a vast, diffuse expanse of gas and plasma. It is a stage where the intricate dance of cosmic forces unfolds. Its study not only deepens our understanding of the universe's structure and history, but also challenges our ability to comprehend the scale and intricacy of cosmic phenomena. Let us delve even deeper into its role, exploring its connections to some of the most profound questions about the universe. One of the most fascinating aspects of the IgM is its relationship with dark energy, the enigmatic force driving the accelerated expansion of the universe. While dark energy operates on the largest scales, its effects are imprinted on the distribution and dynamics of the IgM. As the universe expands, the filaments of the cosmic web stretch, and the IgM within them evolves. Observing how this medium responds to the expansion provides indirect evidence of dark energy's influence. For instance, the clustering of galaxies and the distribution of the IgM offer clues about how dark energy competes with gravitational forces over cosmic time. The thermal history of the IgM is another area of intense study, as it reveals the processes that have shaped the universe since its infancy. The temperature of the IgM has undergone dramatic changes, influenced by events like the epoch of reionization and the formation of galaxy clusters. During reionization, the first generations of stars and galaxies emitted intense radiation that ionized the surrounding hydrogen gas. This process left an indelible mark on the IgM, raising its temperature and altering its state. Studying the remnants of this era in the IgM helps us piece together the timeline of cosmic history. As galaxies formed and evolved, their interactions with the IgM became increasingly complex. Galaxies are not isolated entities. They exist in a constant exchange of matter and energy with their surroundings. Outflows from galaxies, driven by phenomena such as supernova explosions and active galactic nuclei, inject energy and metals into the IgM. These outflows create shockwaves that heat the gas and contribute to the enrichment of the medium with heavy elements. Conversely, the IgM also supplies galaxies with fresh gas, fueling star formation and shaping their growth. This interplay is a cornerstone of cosmic evolution, linking the fates of galaxies to the properties of the IgM. The role of the IgM in shaping the formation of large-scale structures cannot be overstated. The cosmic web, a vast network of filaments and voids, is primarily composed of the IgM. These filaments serve as the scaffolding upon which galaxies and clusters form, guided by the gravitational pull of dark matter. The IgM flows along these filaments, accumulating in dense regions where galaxy clusters emerge. Simulations of cosmic structure formation have revealed the intricate patterns of this web, highlighting the IgM's crucial role in orchestrating the distribution of matter on the largest scales. At the intersections of these filaments, galaxy clusters form, creating some of the most energetic environments in the universe. The intracluster medium, ICM, a denser and hotter counterpart to the IgM, exists within these clusters. The ICM contains high-temperature plasma that emits X-rays, providing a wealth of information about the dynamics and composition of galaxy clusters. While distinct from the ICM shares a deep connection with it, as both are integral components of the larger cosmic ecosystem. The study of the IGM also pushes the boundaries of observational astronomy, requiring innovative techniques and advanced instrumentation. Instruments like the Hubble Space Telescope, the Very Large Telescope, and the upcoming James Webb Space Telescope have been pivotal in uncovering the secrets of the IGM. Observations of distant quasars, gamma-ray bursts, and the cosmic microwave background provide indirect glimpses of the IGM's properties. These observations are complemented by sophisticated simulations, which model the behavior of the IGM under various physical conditions, offering insights that guide and refine our understanding. Moreover, the IGM serves as a natural laboratory for testing fundamental physics. Its extreme conditions, low density, vast scale, and exposure to intense radiation, provide a unique environment for studying phenomena that are difficult to replicate on Earth. For example, the IGM's response to ionizing radiation and shockwaves offers insights into plasma physics and thermodynamics. Additionally, its interactions with cosmic magnetic fields and high-energy particles contribute to our understanding of astrophysical processes on a grand scale. The IGM's importance extends beyond its physical properties. It also holds profound implications for cosmology and our place in the universe. By studying the IGM, we gain insights into the initial conditions of the universe, the processes that have shaped its evolution, and the forces that govern its behavior. This knowledge not only enriches our understanding of the cosmos but also deepens our appreciation for the interconnectedness of all things. The IGM, though invisible to the naked eye, is a reminder that even the most diffuse and seemingly empty regions of space are teeming with activity and significance. As we continue to unravel the mysteries of the IGM, we are reminded of the boundless curiosity that drives scientific exploration. The quest to understand this hidden matter is a journey that challenges our intellect, expands our perspective, and connects us to the broader universe. Through the study of the IGM, we come closer to answering some of the most fundamental questions about existence, from the origins of the universe to the nature of matter and energy. The intergalactic medium is more than just a physical entity. It is a symbol of the universe's vastness and complexity. Its study bridges the gap between the smallest particles and the largest structures, offering a window into the interconnected fabric of reality. The IGM's secrets are still being uncovered, but each discovery brings us closer to a deeper understanding of the cosmos and our place within it. The intergalactic medium, IGM, continues to captivate scientists not just for what it reveals about the universe, but for the mysteries it still hides. One of the key unresolved questions surrounding the IGM is its precise role in the so-called missing baryon problem. While dark matter and dark energy dominate the universe's mass-energy budget, normal matter, composed of protons, neutrons, and electrons, makes up only about 5% of the total. Yet, when astronomers tally up all the normal matter observed in stars, galaxies, and interstellar gas, they fall short of this theoretical prediction. Where is the rest of the universe's ordinary matter? The IGM is a prime suspect in solving this cosmic puzzle. Studies suggest that a significant fraction of the universe's missing baryons resides in the IGM, particularly in its warmer and more diffuse states. This component, often referred to as the warm-hot intergalactic medium, WIM, is composed of highly ionized gas heated to temperatures ranging from tens of thousands to millions of degrees Kelvin. Detecting this elusive matter is a monumental challenge because its diffuse nature and high temperature make it nearly invisible across most wavelengths of light. However, breakthroughs in X-ray and ultraviolet spectroscopy have begun to provide tantalizing evidence of the WIM's existence. One of the methods used to detect the WIM involves studying absorption lines in the spectra of distant quasars. These quasars, which are powered by supermassive black holes in the centers of galaxies, emit bright, high-energy light that travels through vast stretches of the IGM before reaching Earth. As this light passes through the WIM, specific wavelengths are absorbed by ionized elements such as oxygen, carbon, and neon. By analyzing these absorption features, scientists can infer the presence, composition, and temperature of the intervening gas. While these observations are still in their infancy, they have already hinted at a vast reservoir of baryonic matter hidden within the WIM. The study of the WIM also intersects with research on cosmic shocks, which play a crucial role in heating and distributing the IGM. These shocks are generated by large-scale cosmic events, such as galaxy collisions and the growth of massive galaxy clusters. When galaxies merge or when clusters gravitationally pull matter toward them, the infalling gas is compressed and heated, creating shockwaves that propagate through the IgM. These shocks not only heat the gas to extreme temperatures but also stir it, leading to turbulent motions that distribute energy and metals across vast distances. The detection and study of these shocks provide another pathway to understanding the WIM. For instance, high-resolution X-ray observatories like Chandra and XMM Newton have detected faint signals of hot gas in the outskirts of galaxy clusters, where these shocks are most pronounced. Future missions, such as the proposed Athena X-ray Observatory, promise to shed even more light on these processes, potentially mapping the WIM in unprecedented detail. But the IgM is not a static environment, it evolves over cosmic time, shaped by the interplay of various astrophysical processes. During the early stages of the universe, most of the IgM was neutral hydrogen. However, as the first stars and galaxies formed, their intense ultraviolet radiation ionized this gas, initiating the epoch of reionization. This transformative period marked a turning point in the universe's history, as the IgM shifted from being opaque to transparent to light at many wavelengths. The details of this transition, including the timing and sources of reionization, remain subjects of active research. Interestingly, the IgM also acts as a repository for the chemical elements forged within stars. When stars die in supernova explosions, they release heavy elements, or metals, into their surroundings. Some of this material escapes the confines of galaxies, propelled by energetic winds or jets, and eventually enriches the IgM. By studying the metal content of the IgM, scientists can trace the history of star formation and chemical evolution across the universe. Moreover, the IgM serves as a canvas for understanding the influence of cosmic magnetic fields. Although these fields are weak compared to those found in galaxies or stars, they permeate the IgM and play a role in shaping its behavior. Magnetic fields can influence the motion of charged particles, guide the formation of structures within the IgM, and even affect the propagation of cosmic rays. Unraveling the origin and evolution of these magnetic fields is a challenge that requires combining observations, simulations, and theoretical insights. The IgM also provides a unique opportunity to test our understanding of fundamental physics. For instance, the distribution of matter within the IgM offers constraints on the properties of dark matter, particularly on its ability to form small-scale structures. Similarly, the interaction of light with the IgM can reveal subtle effects predicted by quantum mechanics and general relativity, such as gravitational lensing and photon scattering. Another intriguing aspect of the IgM is its potential connection to exotic phenomena, such as fast radio bursts, FRBs. These brief, intense flashes of radio waves are thought to originate from distant galaxies, but their exact causes remain unknown. As FRBs travel through the IgM, they interact with the intervening plasma, imprinting signatures that can be used to study the density and composition of the IgM. By combining FRB observations with other data, scientists can probe the IgM on scales that were previously inaccessible. The IgM challenges us to think about the universe in a holistic way. While galaxies and stars often take center stage in our understanding of the cosmos, the IgM represents the vast interconnected backdrop against which these luminous objects exist. Its study reminds us that even the most seemingly empty spaces are rich with complexity and significance. The mysteries of the intergalactic medium are far from fully unraveled, but each new discovery brings us closer to a comprehensive understanding of the universe's hidden matter. As technology advances and our observational capabilities improve, the IgM will undoubtedly remain a focal point for astrophysical research, offering insights not only into the cosmos but also into the nature of reality itself. The intergalactic medium, IgM, is not only a vast reservoir of hidden matter but also a critical piece in the puzzle of understanding cosmic evolution. As astronomers delve deeper into its mysteries, one emerging area of interest is how the IgM connects and interacts with galaxies. Far from being passive or inert, the IgM actively exchanges matter and energy with galaxies through a complex web of processes. This cosmic exchange is crucial for fueling star formation, regulating galaxy growth, and even shaping the large-scale structure of the universe. Galaxies are not isolated systems. They are embedded in the IGM, which acts as both a supplier and a recipient of material. Gas flows into galaxies from the IGM, providing the raw material for new stars. At the same time, galaxies expel matter back into the IGM through processes such as stellar winds, supernova explosions, and active galactic nuclei (AGN) outflows. These outflows can carry metals, energy, and momentum into the IGM, enriching and energizing it. The interplay between inflows and outflows creates a dynamic feedback loop that governs the evolution of both galaxies and the IGM. One of the most striking manifestations of this interaction is the phenomenon of galactic winds. These powerful outflows of gas are driven by intense star formation, or the activity of supermassive black holes at the centers of galaxies. Galactic winds can extend tens or even hundreds of thousands of light-years into the IGM, carrying with them significant amounts of energy and heavy elements. Observations of these winds provide a direct window into the exchange of material between galaxies and the IGM, revealing how galaxies can influence their larger environment. The IGM also plays a critical role in the growth of galaxy clusters, the largest gravitationally bound structures in the universe. Galaxy clusters contain vast amounts of hot, ionized gas known as the intracluster medium, ICM, which is essentially an extension of the IGM within the cluster's gravitational well. The ICM is heated to tens of millions of degrees Kelvin, making it detectable in X-ray wavelengths. Studying the ICM provides insights into the processes that govern the assembly of galaxy clusters and their interactions with the surrounding IGM. The connection between the IGM and galaxy clusters is further illuminated by the phenomenon of cosmic filaments. These massive, thread-like structures of gas and dark matter span millions of light-years, forming the scaffolding of the universe's large-scale structure. Galaxies and galaxy clusters form at the intersections of these filaments, while the filaments themselves are composed of the diffuse gas of the IGM. Observing these filaments is challenging due to their low density and faint emission, but recent advancements in radio and X-ray astronomy have begun to unveil their properties. These filaments act as conduits, channeling gas and dark matter into galaxies and clusters, fueling their growth over cosmic time. Another key aspect of the IGM's role in cosmic evolution is its impact on the formation and propagation of cosmic rays. These high-energy particles, which originate from supernova explosions, AGN, and other energetic astrophysical events, traverse the IGM on their journey through the universe. The IGM's magnetic fields and turbulence influence the paths of these particles, scattering and slowing them. By studying cosmic rays and their interactions with the IGM, scientists can gain insights into both the properties of the IGM and the sources of these energetic particles. The IGM also serves as a testing ground for understanding the nature of dark matter and dark energy, the two most enigmatic components of the universe. The distribution of matter within the IGM, as traced by absorption lines in quasar spectra, provides constraints on the properties of dark matter, including its ability to form small-scale structures. Similarly, the large-scale distribution of the IGM, as revealed by surveys of galaxies and the cosmic web, offers clues about the effects of dark energy on the expansion of the universe. By combining observations of the IGM with theoretical models, researchers aim to unravel the fundamental nature of these elusive phenomena. One of the most exciting frontiers in IGM research is the use of next-generation telescopes and observatories to probe its properties in unprecedented detail. Instruments such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, promise to revolutionize our understanding of the IGM by providing higher sensitivity and resolution across a range of wavelengths. These facilities will enable astronomers to detect faint signals from the IGM, map its distribution across cosmic time, and explore its interactions with galaxies and other structures. For example, JWST's advanced infrared capabilities will allow scientists to study the IGM during the epoch of reionization, shedding light on how the first galaxies and stars transformed the universe. Meanwhile, the SKA's unparalleled sensitivity to radio waves will enable the detection of neutral hydrogen in the IGM, providing a direct view of its distribution and dynamics. These observations will complement ongoing efforts to study the IGM using X-ray and ultraviolet telescopes, creating a multi-wavelength picture of this hidden component of the universe. Beyond its scientific significance, the study of the IGM also inspires profound philosophical questions about our place in the cosmos. The IGM represents the vast, interconnected fabric of the universe, a reminder that even the emptiest regions of space are filled with complexity and meaning. It challenges us to think beyond the boundaries of galaxies and stars, to consider the universe as a whole and our role within it. As we continue to explore the mysteries of the IGM, we are not only uncovering the secrets of the cosmos but also deepening our understanding of existence itself. The intergalactic medium is a testament to the richness of the universe and the endless possibilities for discovery. Each new observation, each new insight, brings us closer to a more complete understanding of the cosmos, revealing the beauty and intricacy of the hidden matter that surrounds us. The journey to uncover the secrets of the IGM is far from over, and the mysteries that remain promise to keep astronomers and dreamers alike captivated for generations to come. As we continue to unravel the mysteries of the intergalactic medium, IGM, we find ourselves confronted with questions that push the boundaries of both scientific inquiry and human imagination. One of the most intriguing aspects of the IGM is its connection to the overall structure of the universe. The IGM is not just a collection of gas and plasma filling the void between galaxies. It is part of a larger cosmic web that structures the universe itself. This web-like arrangement is known as the cosmic web, and it represents one of the most fundamental patterns in the universe. The cosmic web consists of vast strands of matter, including galaxies, dark matter, and the IGM, which stretch across the universe like a vast network of interconnected filaments. At the intersections of these filaments are galaxy clusters, the most massive structures in the universe. These filaments are not just the passive backdrop of cosmic activity. They are active players in the formation of galaxies, the distribution of dark matter, and the movement of gas and energy throughout the cosmos. The role of the IGM in the cosmic web is to serve as the medium through which matter flows between galaxies and clusters. In many ways, the IGM acts as the bloodstream of the universe, circulating matter and energy across vast distances. The gas within the IGM is constantly moving, driven by gravitational forces, turbulence, and the energy released by stars, black holes, and other celestial objects. This movement is crucial for the exchange of material between galaxies and clusters, and it plays a central role in the ongoing evolution of the universe. As galaxies move through the IGM, they interact with it in ways that can lead to significant changes. For example, the motion of a galaxy through the IGM can create shock waves that heat the surrounding gas, leading to the formation of large, hot regions of plasma. These shock waves can also lead to the creation of cosmic rays, high-energy particles that travel through the IGM and carry information about the processes occurring within galaxies and clusters. At the same time, the IGM is influenced by the movement of galaxies and the gravitational forces exerted by large structures like galaxy clusters. As galaxies fall into clusters, they can compress the surrounding gas, leading to the formation of denser regions of the IGM. These dense regions, known as cold fronts, are often associated with the cooling of gas within clusters and the triggering of new star formation. The interactions between galaxies, the IGM, and the dark matter that fills the cosmic web are responsible for shaping the universe's large-scale structure and driving its evolution. The study of the IGM's role in the cosmic web has also led to important discoveries about the history of the universe. The IGM provides a window into the early universe, allowing astronomers to study the conditions that existed just after the Big Bang. During the early stages of cosmic evolution, the IGM was a hot, dense soup of particles, and as the universe expanded, it cooled, allowing neutral hydrogen to form. This process, known as recombination, occurred about 380,000 years after the Big Bang and marked the beginning of the universe's transition from an opaque, ionized state to the transparent, neutral state we observe today. The study of the IGM also provides valuable insights into the epoch of reionization, a period in the universe's history when the first stars and galaxies formed and began to ionize the hydrogen gas that filled the cosmos. This process played a critical role in shaping the universe as we know it today. By studying the IgM's properties during this era, astronomers can better understand the formation of the first galaxies, the growth of supermassive black holes, and the evolution of the cosmic web. One of the key challenges in studying the IgM is its faintness. Because the gas in the IgM is so diffuse, it emits very little light, making it difficult to observe directly. Instead, astronomers rely on indirect methods to study the IgM, such as observing how light from distant quasars is absorbed as it passes through the gas. This absorption can reveal the density, temperature, and chemical composition of the IgM, providing a detailed picture of its properties across vast distances. To overcome the challenges of studying the IgM, astronomers are developing new techniques and technologies that can probe the gas in unprecedented detail. One of the most promising approaches is the use of next-generation telescopes and observatories, such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA. These advanced instruments will allow scientists to detect faint signals from the IgM across a wide range of wavelengths, providing a more complete understanding of its properties and behavior. The JWST, in particular, is poised to make significant contributions to our understanding of the IgM. With its ability to observe in the infrared, the JWST will be able to study the IgM during the epoch of reionization, providing a direct view of the gas that filled the early universe. By observing the absorption of light from distant quasars and galaxies, astronomers will be able to map the distribution and density of the IgM at different points in time, helping to piece together the history of the universe. Similarly, the SKA, which is designed to detect radio waves, will enable astronomers to study the neutral hydrogen that makes up much of the IgM. Radio waves can penetrate the gas more easily than visible or infrared light, making them an ideal tool for studying the IgM's structure and dynamics. By combining data from the SKA with other observations, scientists hope to create a comprehensive map of the IgM and its role in the formation of galaxies and the evolution of the universe. These new tools and techniques will not only expand our knowledge of the IgM but also open up new avenues for understanding the universe's most fundamental mysteries. For example, the study of the IgM could help answer some of the biggest questions in cosmology, such as the nature of dark matter and dark energy. By mapping the distribution of matter in the IgM, scientists can gain insights into the properties of dark matter, which is thought to make up the majority of the universe's mass. Similarly, the large-scale distribution of the IgM can provide clues about the effects of dark energy, the mysterious force that is driving the accelerated expansion of the universe. In addition to its scientific significance, the study of the IgM also raises philosophical questions about the nature of the universe and our place within it. The IgM serves as a reminder that the universe is not a collection of isolated objects but a vast, interconnected web of matter and energy. It challenges us to think about the universe as a dynamic, ever-evolving system, where the actions of galaxies, stars, and other celestial objects have far-reaching consequences. The more we learn about the IgM, the more we come to realize that the universe is far more complex and interconnected than we ever imagined. The exploration of the IgM is not just about understanding the universe on a technical level. It is also about deepening our understanding of our own place in the cosmos. The IgM serves as a powerful reminder of the scale and interconnectedness of the universe, and as we continue to study it, we gain new insights into the forces that have shaped our existence. The IgM may be hidden from view, but its influence is felt across the universe, and its secrets continue to captivate astronomers and dreamers alike. The further exploration of the intergalactic medium, IgM, is crucial not only for understanding the large-scale structure of the universe but also for uncovering the unseen forces that govern it. As we dive deeper into the study of this mysterious component, we start to see the IgM as more than just a passive backdrop. It becomes an active player in the drama of cosmic evolution. The IgM's presence is felt in everything from the birth of galaxies to the formation of clusters of galaxies, and even the evolution of supermassive black holes. At a basic level, the IgM is largely composed of hydrogen, which in its most common form is neutral. However, in regions of high energy and density, it can become ionized, forming a state of matter known as plasma. This ionized gas is incredibly important for understanding the energetic processes at play across vast cosmic scales. Plasmas are not just any ordinary gases. They exhibit unique properties that allow them to conduct electricity, create magnetic fields, and participate in the formation of cosmic structures like stars and galaxies. What's particularly fascinating about the IgM is its role in the evolution of galaxies. It's not just that galaxies exist within the IgM, it's that the medium itself can influence their formation and development. The interaction between galaxies and the IgM can be dramatic. For instance, as galaxies travel through the diffuse gas, they can strip away parts of their own gas. This process, known as ram pressure stripping, happens when a galaxy moves through the IgM at high speeds, and the gas within the IgM pushes against the gas in the galaxy, causing it to be ejected into space. This phenomenon can have a profound impact on a galaxy's ability to form new stars because the gas is essential for star formation. Without it, galaxies can be prevented from creating new stars, leaving them to slowly fade away. The IgM can also contribute to the formation of new galaxies. The gas between galaxies is not uniform. It has regions of varying density, and in areas where the gas is denser, gravitational forces can cause clumping. These clumps of gas can then become gravitationally bound, forming the seeds for the creation of new galaxies. Essentially, the IgM is the birthplace of galaxies in some ways, providing the raw material and the environment necessary for galaxy formation to take place. This process is tied to a much larger phenomenon known as cosmic inflation, which occurred in the very early universe. During this period, the universe expanded exponentially in just a fraction of a second, and the tiny fluctuations that were present in the early universe's density patterns were stretched across vast distances. These fluctuations are seen today as the seeds of large-scale structures like galaxy clusters and superclusters, all connected by vast filaments of the IgM. These filaments, part of the cosmic web, are the highway through which galaxies and other cosmic structures are connected. Furthermore, the IgM plays an essential role in the behavior of dark matter. We don't fully understand dark matter yet, but we do know it interacts with the gravitational fields of galaxies and clusters. Some theories suggest that dark matter could be lurking in the IgM itself, possibly influencing the behavior of the gas and plasma in ways that we have yet to fully comprehend. While we are still far from solving the mystery of dark matter, understanding how it interacts with the IgM could provide a significant clue about its nature and its role in shaping the universe. In addition to its physical properties, the IgM also holds important information about the history of the universe, particularly in terms of cosmic evolution. As we look back in time through the study of distant quasars and galaxies, the IgM provides a lens through which we can understand the early universe. Light from these distant objects passes through the IgM, leaving behind a signature of absorption lines that tell astronomers about the gas through which it has traveled. By studying these absorption lines, we can learn about the composition, temperature, and density of the IgM at different points in the universe's history. This method of studying the IgM is one of the key ways astronomers have been able to study the epoch of reionization, a crucial period in the universe's history when the first stars and galaxies began to form and reionize the hydrogen gas that filled the cosmos. This epoch of reionization, which occurred roughly 13 billion years ago, marks the transition from a dark, opaque universe to one that is bright and transparent. During this period, ultraviolet light from the first stars and galaxies broke up the hydrogen atoms in the IgM, creating a universe that was once again transparent to radiation. This process was a pivotal moment in cosmic history, and understanding the IgM's role in it has been a key objective for astronomers. The study of the IgM also opens doors to understanding other cosmic phenomena. For example, the IgM interacts with the intense radiation emitted by quasars, the energetic centers of distant galaxies. The radiation from quasars can ionize the gas in the IgM, leaving an imprint on the light that travels through it. These imprints allow astronomers to study not only the IgM itself but also the quasars and galaxies that are responsible for shaping the universe. The study of this gas also helps to shed light on the role of black holes. Supermassive black holes, which reside at the centers of most galaxies, have an immense influence on their surroundings. As they consume matter, they release vast amounts of energy in the form of radiation and powerful outflows of gas and plasma. These outflows can have a profound effect on the IgM, heating it to extreme temperatures and potentially contributing to the ionization of the gas. The energetic activity around these black holes influences the formation of galaxies and the evolution of the IgM itself. By studying how black holes interact with the IgM, astronomers can better understand the coevolution of galaxies and their central black holes. Another fascinating aspect of the IgM is its contribution to our understanding of dark energy. Dark energy, the mysterious force that is driving the accelerated expansion of the universe, has long puzzled scientists. Some theories suggest that the distribution and behavior of the IgM could provide clues to understanding dark energy. If the IgM is influenced by dark energy in some way, studying its properties could give us insight into the nature of this elusive force. We also need to address the role of cosmic rays in the IgM. Cosmic rays are high-energy particles that travel through space, and they can interact with the IgM in interesting ways. These interactions can lead to the creation of additional energy, and can even contribute to the heating of the gas in the IgM. Cosmic rays also play a key role in the ionization of the IgM, further influencing its evolution and behavior. The IgM is also intimately connected with other forms of cosmic energy, such as the energy released by star formation and supernovae. Stars are born out of the gas in the IgM, and their death, in the form of supernova explosions, releases vast amounts of energy that can shock the surrounding gas. This energy release can heat the IgM, contribute to the formation of larger structures like galaxy clusters, and even trigger the formation of new stars. By continuing to study the IgM, we can unlock further mysteries of the universe. Every discovery made about the IgM brings us one step closer to understanding how the universe evolved from the Big Bang to the vast, complex structure we see today. From its role in galaxy formation to its connection to the mysterious forces of dark matter and dark energy, the IgM is far more than just an empty void. It is a dynamic, ever-changing medium that plays a crucial role in the grand cosmic story. The intergalactic medium is not just a concept confined to the textbooks of astrophysics. It is a vital, vibrant part of the universe. It's a hidden force, often invisible to the naked eye, but it shapes the very nature of everything around us. Understanding the IgM is not just an academic pursuit. It's an exploration of the forces that have driven the universe's growth and continue to shape its future. The more we learn about the IgM, the more we realize how interconnected and vast the universe truly is, offering endless possibilities for future discoveries. As we continue exploring the hidden depths of the intergalactic medium, IgM, we uncover more mysteries about the structure and composition of the universe. The IgM, as the vast space between galaxies, is not merely a quiet, unremarkable void but a bustling expanse of gas, plasma, and dark matter that is crucial to understanding cosmic processes. This region of space is more than just a backdrop for cosmic events. In fact, it holds the key to many unanswered questions in modern astronomy and astrophysics. One of the most exciting areas of research is the relationship between the IgM and the larger structures in the universe, such as galaxy clusters, superclusters, and the cosmic web. These gigantic structures are interconnected by vast filaments of the IgM, often referred to as the cosmic web. These filaments are composed of hot, ionized hydrogen gas, which stretches across billions of light years. When we study the IgM, we are essentially studying the cosmic highways that link together galaxies and galaxy clusters across the vast reaches of space. The discovery of the cosmic web was groundbreaking because it gave astronomers the first direct evidence that the universe is not simply a random scattering of galaxies but a highly structured, interconnected network of matter. The cosmic web is not a random collection of material. It is a dynamic and organized structure that has been shaped by gravity over billions of years. The IgM plays a crucial role in this structure by serving as the medium through which galaxies and galaxy clusters are connected. In addition to its role in the cosmic web, the IgM is also integral to the study of galaxy evolution. As we have already discussed, galaxies are born in the dense regions of the IGM, where gas clouds collapse under the force of gravity. Over time, these gas clouds coalesce to form stars, and eventually, galaxies. The interaction between galaxies and the IGM continues throughout their lifetimes, influencing their development and behavior. For example, the gas in the IGM can fuel star formation within galaxies, or, conversely, it can strip galaxies of their gas, preventing them from forming new stars. This ongoing interaction between galaxies and the IGM is a fundamental aspect of galaxy evolution. The IGM also contributes to our understanding of how large-scale cosmic structures form. The process of structure formation in the universe is driven by the interplay between gravity and the distribution of matter, including dark matter, gas, and plasma. The IGM, with its vast and diffuse nature, acts as the glue that binds together the material that forms these structures. By studying the distribution and behavior of the IGM, astronomers can gain insights into the forces that shape the universe's largest structures. However, there is still much we don't know about the IGM. Despite being such a dominant feature of the universe, it remains elusive in many ways. One of the challenges in studying the IGM is that it is incredibly diffuse. The gas in the IGM is spread out over vast distances, making it difficult to observe directly. It's not dense like the gas in stars or galaxies, and it's not bright enough to be visible with traditional optical telescopes. Instead, astronomers rely on indirect methods, such as studying the absorption lines in the light from distant quasars or using radio telescopes to detect the faint emissions of the IGM. One of the key questions that remains unanswered is how the IGM's composition has changed over time. In particular, how has it evolved since the Big Bang? Early in the history of the universe, the IGM was primarily made up of neutral hydrogen, and it was opaque to radiation. As the universe expanded and cooled, the first stars and galaxies began to form, emitting light that ionized the hydrogen in the IGM. This process, known as reionization, allowed light to travel freely through the universe, making the cosmos transparent. But the exact timeline and mechanisms behind reionization are still a matter of active research. Reionization is thought to have occurred between 400 million and 1 billion years after the Big Bang, during a period known as the Epoch of Reionization. During this time, the first sources of light, the first stars, galaxies, and quasars, emitted ultraviolet radiation that ionized the hydrogen in the IGM. This process transformed the IGM from a dense, neutral gas into a largely ionized plasma. Understanding the timeline and processes involved in reionization is crucial for understanding the formation of the first stars and galaxies and the evolution of the universe's large-scale structure. In addition to reionization, another important aspect of the IGM is its temperature. The gas in the IGM is incredibly hot, with temperatures reaching millions of degrees Celsius. This heat is primarily generated by the interaction between the IGM and other cosmic objects, such as supermassive black holes, quasars, and galaxy clusters. The hot gas in the IGM is thought to be the source of the X-ray emissions detected by space telescopes like Chandra and XMM Newton. By studying the temperature of the IGM, astronomers can learn more about the energy processes occurring in the universe's most energetic environments. The study of the IGM is also closely tied to the study of dark matter and dark energy. While the IGM itself is made up of ordinary matter, its interaction with dark matter and dark energy could provide crucial insights into the nature of these mysterious substances. For example, some theories suggest that dark matter could be interacting with the IGM in ways that we have not yet fully understood. Similarly, dark energy, which is thought to be responsible for the accelerated expansion of the universe, may be influencing the behavior of the IGM. The study of the IGM could, therefore, provide a window into the nature of dark matter and dark energy, two of the most fundamental mysteries in modern physics. Another intriguing aspect of the IGM is its relationship with cosmic rays. Cosmic rays are high-energy particles that travel through space, and when they interact with the IGM, they can create new particles and radiation. The study of cosmic rays and their interactions with the IGM can help astronomers learn more about the high-energy processes occurring in the universe. Cosmic rays are also thought to play a role in the ionization of the IGM, further complicating the relationship between the medium and its surrounding environment. The role of the IGM in the formation of large-scale structures is another area of active research. While galaxies and galaxy clusters are the most obvious components of the universe's large-scale structure, the IGM plays a vital role in shaping the way these structures form. The gas in the IGM is not evenly distributed, and its density varies across different regions of space. This variation in density can influence the way that galaxies and clusters of galaxies form, grow, and interact with one another. The IGM is also intimately connected with the process of galaxy cluster formation. Galaxy clusters are some of the largest structures in the universe, and they are made up of hundreds or thousands of galaxies. The gas in the IGM plays a key role in the formation of these clusters. As galaxies collide and merge, they pass through the IGM, creating shock waves and heating the gas to extremely high temperatures. This heating process is responsible for the X-ray emissions detected from galaxy clusters, and it also plays a role in the formation of the intracluster medium, ICM, the hot gas that fills the space between galaxies in a cluster. The intergalactic medium is a vital component of the universe, and its study is key to understanding the fundamental processes that shape the cosmos. From its role in the formation of galaxies and the large-scale structure of the universe to its influence on the behavior of dark matter, dark energy, and cosmic rays, the IGM is a central player in the cosmic drama. While there is still much to learn about the IGM, every discovery brings us one step closer to understanding the universe in its entirety. The mysteries of the IGM, much like the rest of the cosmos, are waiting to be uncovered, and as we continue to study it, we will unlock more secrets of the universe's origin, evolution, and ultimate fate. As we continue to explore the complexities of the intergalactic medium, IGM, it's important to consider how new technologies and advancements in observational techniques are allowing us to probe deeper into this elusive realm of space. The IGM has long been difficult to study due to its diffuse nature and its faint signals, but with the development of more advanced telescopes and instruments, we are now able to peer into its mysteries like never before. These advancements are not only helping us answer existing questions about the IGM, but they are also raising new questions and opening up new avenues for exploration. One such advancement is the use of highly sensitive radio telescopes. The IGM is primarily composed of hydrogen, which is transparent to visible light but interacts strongly with radio waves. This makes the IGM an excellent subject for study using radio telescopes, especially those capable of detecting the faint emissions from the gas in the medium. By observing the IGM in radio wavelengths, astronomers can learn more about the temperature, density, and ionization state of the gas, as well as uncover hidden features of the cosmic web. In particular, the 21 cm line of hydrogen is one of the most important tools for studying the IGM. This specific frequency of radio waves is emitted by neutral hydrogen, which makes up a significant portion of the IGM. By detecting the 21 cm line, astronomers can map out the distribution of hydrogen across vast regions of space and even trace the evolution of the IGM over cosmic time. This allows us to better understand not only the state of the IGM today but also how it has changed since the early universe. One of the key goals of current and future radio astronomy projects is to study the epoch of reionization in greater detail. As we've discussed earlier, this was the period when the first stars and galaxies began to form and ionize the hydrogen in the IGM, making the universe transparent. This period of cosmic history is crucial for understanding the origins of galaxies, stars, and the large-scale structure of the universe. However, due to the vast distances involved, observing this period directly is incredibly difficult. By studying the 21 cm line and other emissions from the IGM, astronomers hope to gain new insights into the timing and nature of reionization, shedding light on one of the most important events in the universe's history. Another breakthrough in studying the IGM comes from observations in the X-ray spectrum. As we mentioned earlier, the gas in the IGM is extremely hot, reaching temperatures of several million degrees Celsius in many regions. These high-energy environments emit X-rays, which can be detected by space-based telescopes like Chandra and XMM Newton. By studying the X-ray emissions from the IGM, scientists can learn about the distribution of hot gas across the universe, and how this gas is heated and ionized by interactions with galaxies, supermassive black holes, and other cosmic phenomena. X-ray observations also provide important clues about the composition of the IgM. While hydrogen makes up the majority of the gas in the IgM, there are also traces of other elements, such as helium, oxygen, and carbon. By analyzing the X-ray spectra from the IgM, scientists can determine the abundance of these elements and their distribution across space. This helps us understand the processes by which elements are created and distributed throughout the universe, as well as how the IgM has evolved over cosmic time. One of the most exciting discoveries in recent years involves the detection of large-scale cosmic structures within the IgM. These structures, such as galaxy filaments and voids, have long been suspected to exist, but their exact nature and distribution were not well understood. Using advanced simulations and observations, astronomers have now been able to map out these structures in detail. These structures are not just random collections of matter, they are intricately connected, and their formation is governed by the same gravitational forces that drive the evolution of galaxies and clusters. The largest of these cosmic structures, the cosmic web, is a vast network of gas and galaxies stretching across billions of light-years. The IgM serves as the medium through which this web is connected, and its role in shaping the large-scale structure of the universe cannot be overstated. By studying the cosmic web, astronomers can gain a better understanding of how the universe has evolved over time, and how the gravitational forces between galaxies and galaxy clusters have influenced the growth of these large-scale structures. Moreover, the IgM is essential to understanding the distribution of dark matter in the universe. Dark matter, which makes up around 27% of the universe's total mass, is thought to interact with normal matter only through gravity and possibly through weak interactions. While dark matter itself is invisible and undetectable by conventional means, its presence can be inferred through its gravitational effects on visible matter. The IgM plays a crucial role in the distribution of dark matter, as its gravitational influence helps shape the structure of the universe. By studying the IgM's interactions with dark matter, scientists can learn more about the nature of dark matter itself and how it has influenced the formation of galaxies, clusters, and the cosmic web. The relationship between the IgM and dark energy is another area of active research. Dark energy is a mysterious force that is driving the accelerated expansion of the universe, and while much is known about its effects, its true nature remains one of the most significant unsolved mysteries in modern physics. One possibility is that dark energy is influencing the behavior of the IgM, perhaps by affecting the rate of expansion of the universe or the distribution of gas in the IgM. Understanding how the IgM interacts with dark energy could provide vital clues about the ultimate fate of the universe and help resolve some of the most fundamental questions in cosmology. Furthermore, the IgM plays a key role in our understanding of galaxy formation and evolution. Galaxies are born in regions of higher gas density, where gravitational collapse leads to the formation of stars. However, the interaction between galaxies and the IgM is far from straightforward. As we have seen, the IgM can fuel star formation within galaxies, but it can also strip gas from galaxies, preventing them from forming new stars. This delicate balance between galaxy growth and gas loss is a crucial aspect of the life cycle of galaxies, and the IgM is at the heart of this process. The process of galactic feedback is another important aspect of galaxy evolution that involves the IgM. Feedback occurs when energy from stars or supermassive black holes in a galaxy is released into the surrounding environment, often in the form of powerful winds or radiation. This energy can interact with the IgM, heating it up, ionizing it, and driving gas away from the galaxy. This process can regulate the growth of galaxies by limiting their ability to form new stars. By studying the feedback between galaxies and the IgM, astronomers can better understand how galaxies evolve and how their growth is regulated by their environment. In recent years, the study of the IgM has become increasingly interconnected with the study of black holes, particularly supermassive black holes found at the centers of most galaxies. These black holes are not just passive objects but are active participants in the evolution of their host galaxies. They can influence the surrounding IgM by emitting powerful jets of radiation and particles that interact with the gas in the medium. These interactions can lead to the heating and ionization of the IgM, and they can also play a role in the formation of large-scale cosmic structures. Understanding how supermassive black holes interact with the IgM is crucial for understanding the complex dynamics of galaxy evolution. The presence of active galactic nuclei, AGN, regions of intense radiation and particle outflows at the centers of galaxies, is another key factor in the behavior of the IgM. AGN are thought to be powered by the accretion of matter onto supermassive black holes, and the energy released by this process can have profound effects on the surrounding IgM. AGN can inject vast amounts of energy into the IgM, driving shock waves, heating gas, and altering the structure of the cosmic web. By studying AGN and their interaction with the IgM, astronomers can gain valuable insights into the processes that govern galaxy formation and evolution. As we continue to delve into the complexities of the intergalactic medium, IgM, it becomes clear that this diffuse and elusive substance holds the key to understanding not just the present state of the universe but also its origins and ultimate fate. We've seen how the IgM serves as the connective tissue of the universe, linking galaxies, clusters, and vast cosmic structures through its gas and plasma. The IgM isn't just a passive medium, it actively influences the formation, evolution, and interaction of cosmic structures, making it essential to understanding the universe's grand design. One of the most exciting aspects of studying the IgM is its potential to uncover new physics. The interactions within the IgM are governed by the laws of thermodynamics, magnetohydrodynamics, and general relativity, but there's still so much that we don't understand about these interactions. For example, the IgM contains a vast amount of hot gas, but how this gas is heated and maintained at such high temperatures is still a topic of intense study. It's clear that the IgM isn't just a passive relic of the universe's past but is actively participating in the ongoing evolution of cosmic structures. The temperature of the IgM is a critical component of this understanding. As we've previously discussed, the IgM can reach temperatures of millions of degrees Celsius, particularly in regions where it's heated by processes like cosmic shock waves, supernova explosions, or the radiation from active galactic nuclei, AGN. However, this temperature is not uniform across the entire IgM. Some regions of the IgM are much hotter than others, and understanding the temperature gradients within the medium can provide insights into the dynamics of the universe on the largest scales. One theory is that the hot gas in the IgM is heated by the process of shock heating. Shock waves occur when massive cosmic events, such as galaxy collisions or the activity of supermassive black holes, send shock fronts through the gas, compressing and heating it. These shock waves can travel vast distances, influencing the temperature and density of the IgM. By studying the effects of shock heating, astronomers can gain a deeper understanding of the processes that drive the evolution of cosmic structures and the formation of galaxies and clusters. Another important aspect of the IgM is the magnetic fields that permeate it. Magnetic fields are a fundamental part of astrophysical processes, and they play a significant role in shaping the behavior of plasma in the IgM. The origin of these magnetic fields, their strength, and how they influence the movement of gas and cosmic structures are all topics of active research. Magnetic fields in the IgM can affect everything from the formation of stars and galaxies to the propagation of cosmic rays. By studying these fields, scientists can gain a better understanding of the interplay between magnetic forces, gravity, and plasma dynamics. Magnetic fields are also crucial to the study of cosmic rays, high-energy particles that travel across vast distances in space. These particles, often accelerated by supernovae, active galactic nuclei, and other energetic phenomena, interact with the magnetic fields in the IgM, producing a variety of observable effects. Cosmic rays are important not only because they provide insights into the energetic processes occurring in the universe but also because they can help us understand the nature of dark matter and dark energy, which remains some of the greatest mysteries in modern physics. The study of cosmic rays is also linked to the study of high-energy astrophysical phenomena, such as gamma-ray bursts, GRBs, and X-ray binaries. These violent and energetic events often take place within galaxies or in the vicinity of supermassive black holes, and their radiation can interact with the IgM in ways that are still not fully understood. By studying the interactions between cosmic rays, gamma-ray bursts, and the IgM, scientists hope to gain new insights into the processes that govern the evolution of the universe. Moreover, the presence of gas in the IgM plays an essential role in the formation and evolution of galaxies. The gas that fills the IgM is not only a medium through which cosmic structures interact but is also a potential source of fuel for star formation. When gas from the IgM flows into galaxies, it can contribute to the birth of new stars. However, the process is more complicated than it may seem. The gas in the IgM is often ionized, meaning that it has lost its electrons due to the intense radiation from stars and galaxies. In this state, the gas is less likely to cool and condense into dense clumps that can form stars. Astronomers are still trying to figure out how this ionized gas is able to cool down and collapse to form stars. One possibility is that the gas in the IgM is heated by shock waves or other high-energy processes, and as it cools, it condenses into dense clouds that can collapse under gravity to form stars. However, this process is still poorly understood, and much more research is needed to fully comprehend the dynamics of gas cooling and star formation in the IgM. The role of the IgM in galaxy formation is also intricately linked to the process of galactic feedback. As galaxies form and evolve, they can release large amounts of energy into the surrounding environment, a process known as feedback. This energy can come in the form of radiation, winds, or outflows driven by supernova explosions or the activity of supermassive black holes. These feedback mechanisms can have profound effects on the surrounding IgM, either heating it up, pushing it out of the galaxy, or enriching it with new elements. Feedback from galaxies can also influence the rate of star formation within those galaxies. For example, if a galaxy is pumping out too much energy into the surrounding IgM, it may be unable to form new stars because the gas is heated to the point where it cannot cool and condense. Conversely, if a galaxy is able to accrete more gas from the IgM, it may experience a burst of star formation. The balance between these processes is crucial to the growth and evolution of galaxies, and the IgM plays a key role in maintaining that balance. In addition to galactic feedback, the IgM is also affected by the feedback from supermassive black holes. These supermassive black holes are found at the centers of most galaxies, and their activity can have a profound impact on the surrounding IgM. When a supermassive black hole actively accretes matter, it releases huge amounts of energy in the form of radiation and powerful jets of particles. This energy can interact with the gas in the IgM, heating it up, ionizing it, or even driving gas away from the galaxy entirely. These processes are thought to play a key role in regulating the growth of galaxies and the distribution of gas in the universe. One of the most exciting areas of research in this field is the study of the IgM in relation to galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, all embedded in a vast halo of hot, diffuse gas known as the intracluster medium, ICM. The ICM is closely related to the IgM, as it is composed of gas that lies between galaxies within a cluster. By studying the ICM and its interaction with the IgM, astronomers can learn more about the dynamics of galaxy clusters and the role that the IgM plays in their formation and evolution. As galaxy clusters grow and evolve, the gas within them is influenced by a variety of processes, including the infall of gas from the IgM, interactions between galaxies, and the heating effects of supermassive black holes. These processes can lead to a variety of observable effects, such as the stripping of gas from galaxies, the formation of large-scale shock waves, and the enrichment of the IgM with heavy elements. By studying these effects, astronomers can learn more about the history of galaxy clusters and the role that the IgM plays in their growth. As we continue exploring the intergalactic medium, IgM, we find that this hidden and enigmatic component of the universe holds crucial insights into the larger cosmic evolution. It is essential to recognize that the IgM is not just a passive backdrop but an active participant in the ongoing transformation of the universe. The gas and plasma that make up the IgM interact with galaxies, clusters, and cosmic radiation in ways that shape the very fabric of our universe. One of the most remarkable aspects of the IGM is its interaction with the process of cosmic reionization. This period, which occurred roughly 13 billion years ago, marks a critical transition in the early universe. During this time, the universe shifted from being opaque to transparent, as the first stars and galaxies began to form and emit high-energy radiation that ionized the gas in the IGM. Before reionization, the universe was filled with neutral hydrogen gas, which absorbed light, making the universe a foggy, impenetrable place. But once the first stars and galaxies began to shine, their ultraviolet radiation stripped electrons from the hydrogen atoms, creating an ionized state that allowed light to travel freely across the universe. This dramatic transformation in the IGM allowed the universe to become transparent, enabling light from distant galaxies and quasars to reach us, thus opening the window to the distant past. Reionization is an event that still fascinates astronomers because it provides a unique window into the early universe. While the exact details of this process remain unclear, the IGM holds key information about the conditions that led to this remarkable shift. By studying the properties of the IGM, such as its temperature, density, and ionization state, scientists can reconstruct the timeline of reionization and gain a better understanding of how the first galaxies and stars formed. Observations of the IGM can also help determine the sources of ionizing radiation, whether they were massive stars, black holes, or something else entirely. The study of the IGM also extends beyond the relatively recent history of the universe. It allows us to look back at some of the earliest moments of the cosmos. For example, by studying the absorption of light from distant quasars, astronomers can map the distribution of gas in the early universe. The IGM's interaction with this light can tell us about the temperature and density of the gas, as well as its chemical composition. These observations are key in understanding the processes that occurred in the universe's infancy and provide insight into the formation of the first structures in the cosmos. Looking at the larger picture, the IGM also plays a critical role in our understanding of dark matter and dark energy. While we know that dark matter makes up roughly 27% of the universe's mass, it is invisible and can only be detected by its gravitational effects. Dark matter is thought to interact weakly with ordinary matter, and it doesn't emit or absorb light. This means that it is extremely difficult to study directly, but its presence is inferred from the behavior of galaxies, galaxy clusters, and large-scale cosmic structures. However, by observing the IGM and its interactions with other forms of matter and radiation, scientists are hoping to uncover more clues about the elusive nature of dark matter. Similarly, dark energy, which is believed to make up about 68% of the universe's energy density, remains largely mysterious. It is thought to be responsible for the accelerated expansion of the universe, but its exact nature and properties are still unknown. The IGM plays a role in the study of dark energy because the expansion of the universe influences the density and distribution of gas in the IGM. By studying how the IGM evolves over time, scientists hope to gain insight into the underlying forces driving the accelerated expansion of the universe. As the universe continues to expand, the IGM itself is stretching and evolving, providing a cosmic record of how the universe has changed over billions of years. As we attempt to understand the dark side of the universe, the IGM presents both challenges and opportunities. One of the more intriguing aspects of the IGM is its potential connection to dark matter. Since the IGM is composed of gas that is distributed across vast cosmic distances, it is difficult to directly detect or observe its physical properties, and the interactions between ordinary matter and dark matter are still a subject of much debate. However, some scientists believe that dark matter might interact with the gas in the IGM in ways that we are only beginning to understand. One potential connection lies in the behavior of cosmic rays. Cosmic rays are high-energy particles that are constantly bombarding the Earth and other objects in the universe. These particles come from a variety of sources, such as supernovae, active galactic nuclei, and other high-energy astrophysical events. Some researchers hypothesize that dark matter might be interacting with the IGM in a way that produces cosmic rays. If this hypothesis is correct, it would open up an entirely new avenue of research into the nature of dark matter and its interactions with the rest of the universe. The potential influence of dark matter on the IGM is also evident when studying galaxy clusters. These massive structures contain vast amounts of gas, and the gravitational pull of the dark matter within these clusters plays a significant role in shaping the distribution of the gas. The distribution of gas in galaxy clusters is not uniform, and there are regions where the gas is compressed and heated to extremely high temperatures. These regions, known as the intracluster medium, ICM, are thought to be influenced by the presence of dark matter, which may be responsible for the observed patterns of gas distribution and temperature in these clusters. As we look deeper into the structure of the IGM, it becomes clear that this medium is much more than just a void between galaxies. It is an active and dynamic component of the universe that shapes the formation and evolution of galaxies, stars, and large-scale cosmic structures. The IGM's role in the cosmic web, the vast network of galaxies, clusters, and dark matter that spans the universe, cannot be understated. By understanding the IGM, we can gain a better understanding of how the universe operates on the largest scales, from the birth of galaxies to the expansion of the universe itself. In addition to providing insights into the fundamental forces of the universe, the IGM also presents unique opportunities for technological advancements. The study of cosmic radiation, for example, has led to the development of advanced detection techniques that can be applied to a wide range of scientific fields. By observing the effects of the IGM on light passing through it, scientists can learn more about the universe's large-scale structure, and, in doing so, develop more accurate models of cosmological evolution. The study of the IGM also holds promise for the future of space exploration. As humanity ventures farther into space, understanding the properties of the IGM will be essential for planning missions to distant stars and galaxies. The IGM's role in shielding galaxies from harmful radiation, regulating star formation, and providing the fuel for future stars makes it an integral part of the cosmic ecosystem. Additionally, understanding the role of the IGM in galaxy clusters could lead to better predictions about the behavior of these clusters over time, which could help astronomers and space agencies plan more effective space missions. At its core, the IGM is a cosmic puzzle, full of hidden clues and mysteries waiting to be solved. It connects the very fabric of the universe, influencing the formation of galaxies and clusters while playing a critical role in the evolution of the cosmos. As technology advances and our understanding of the universe deepens, the secrets of the IGM will slowly be unveiled, providing us with a deeper appreciation of the universe's true nature. The IGM holds the key not only to understanding the universe's past but also to unlocking the mysteries of its future. As we continue to peel back the layers of mystery surrounding the intergalactic medium, IGM, it becomes clear that this cosmic fog holds answers to some of the deepest questions in astrophysics. One of the most significant contributions of the IGM to our understanding of the universe is its connection to the formation of large-scale structures. These structures, which include galaxies, galaxy clusters, and vast cosmic filaments, are the backbone of the universe's architecture. The IGM plays a pivotal role in shaping how these structures form and evolve over time. The cosmic web, a vast network of galaxies and dark matter connected by threads of gas, is a visual representation of the universe's large-scale structure. It is in this web where the IGM resides, filling the spaces between galaxies and clusters, binding everything together. The gas in the IGM is not evenly distributed. Rather, it is arranged in filaments, sheets, and voids, which are critical in understanding how galaxies and clusters are formed. In regions where the gas is dense, the gravitational pull of dark matter and the gas itself causes matter to accumulate, leading to the formation of galaxies and clusters. In areas of low gas density, we find voids, vast expanses of space almost completely devoid of matter. These voids are not empty but are filled with a diffuse gas that is incredibly sparse, often referred to as the cosmic void gas. The formation of the cosmic web and the distribution of the IGM is thought to be the result of the universe's expansion. In the early universe, matter was more evenly distributed, but as the universe expanded, regions with slightly more matter began to collapse under their own gravity, forming the first stars and galaxies. The IgM played a key role in this process by acting as a medium in which matter could accumulate, eventually giving rise to the structures we see today. The study of these structures helps scientists understand the forces at play in the early universe and the fundamental mechanisms behind galaxy formation. One of the ways scientists study the IgM and its impact on galaxy formation is through the observation of cosmic simulations. These simulations use supercomputers to model the behavior of the universe over billions of years, providing insights into how galaxies, clusters, and the IgM itself evolve. By comparing the results of these simulations with observational data from telescopes, astronomers can refine their models of cosmic evolution and gain a deeper understanding of how the IgM interacts with galaxies and dark matter. The IgM also plays a crucial role in the ongoing processes within galaxy clusters. These clusters, which are some of the largest structures in the universe, contain hundreds or even thousands of galaxies bound together by gravity. The gas within these clusters, known as the intracluster medium, ICM, is a key component in understanding the dynamics of these massive objects. The ICM is extremely hot, with temperatures reaching millions of degrees Celsius, and it emits X-rays that can be detected by telescopes. The gas in the ICM is not only influenced by the galaxies within the cluster, but also by the dark matter that makes up the majority of the cluster's mass. The IgM's interactions with the ICM can reveal valuable information about the cluster's evolution and the role that dark matter plays in shaping its structure. As we look deeper into the IgM, it becomes evident that its study has far-reaching implications for our understanding of fundamental physics. One of the most exciting possibilities is the potential for discovering new particles or forces that could explain some of the universe's most perplexing mysteries. For instance, some scientists have proposed that dark matter might interact with the gas in the IgM in ways that we have yet to fully understand. If this is true, it could provide critical insights into the nature of dark matter and its role in shaping the universe. The IgM, therefore, could serve as a cosmic laboratory for testing theories about the fundamental forces and particles that govern the universe. In addition to dark matter, the IgM might also hold clues about the nature of dark energy. Dark energy, which is believed to be responsible for the accelerated expansion of the universe, remains one of the most significant unknowns in modern physics. Some scientists have speculated that the IgM could provide insights into dark energy's effects on the expansion of the universe. By studying the distribution and behavior of the gas in the IgM, researchers may be able to develop better models of how dark energy influences cosmic expansion. The study of the IgM also holds promise for future space exploration. As we push the boundaries of our knowledge of the universe, understanding the properties and behavior of the IgM will be crucial for planning missions to distant stars and galaxies. The IgM's role in shaping the evolution of galaxies and clusters makes it an essential part of the cosmic ecosystem. Exploring the IgM will not only help us understand the distant past of the universe but also provide critical information for our future journey into the cosmos. In the next frontier of space exploration, understanding the IgM may play a key role in the development of new technologies. For instance, advancements in detecting and studying the radiation emitted by the IgM could lead to breakthroughs in our ability to detect distant galaxies and star systems. This technology could open up new possibilities for deep space exploration, enabling us to peer into the most distant corners of the universe and uncover hidden mysteries that have remained beyond our reach. Similarly, understanding the role of the IgM in shielding galaxies from harmful radiation could be crucial for planning future missions to habitable exoplanets or other potentially life-supporting environments in the universe. One of the more tantalizing aspects of the IgM is its potential for uncovering information about the very nature of the universe. The gas in the IgM is thought to be the remnant of the early universe, left over from the Big Bang. By studying this gas, scientists hope to answer some of the most profound questions about the origins of the universe. For example, by examining the chemical composition of the IgM, astronomers can learn more about the first elements that formed in the early universe and the processes that led to the creation of the first stars and galaxies. This can help scientists understand the chemical evolution of the universe and provide insights into the formation of the first cosmic structures. The IGM also offers a unique perspective on the universe's future. As we study how the gas in the IGM evolves over time, we can gain insight into the long-term fate of the universe. The evolution of the IGM will be influenced by the same forces that govern the universe's expansion, such as dark energy and dark matter. By understanding how the IGM behaves in different regions of the universe, scientists can develop more accurate predictions about the universe's future. Whether the universe will continue to expand indefinitely or eventually contract is still an open question, but the IGM's role in this process makes it an essential piece of the cosmic puzzle. As we continue to unravel the mysteries of the IGM, we are also uncovering new questions and challenges. While we have made significant progress in understanding this elusive component of the universe, much remains unknown. The gas in the IGM is incredibly diffuse, making it difficult to study directly, and its interactions with dark matter and dark energy are still poorly understood. However, with advancements in observational technology and computational methods, we are beginning to see the first glimpses of the IGM's true nature. These insights are opening up new avenues for research and promising to reveal even deeper mysteries about the universe and its evolution. As we continue to explore the vast and mysterious expanse of the intergalactic medium, IGM, it is important to understand just how profound its role is in the grand scheme of the cosmos. In many ways, the IGM is the universe's silent architect, helping shape the vast structures of the cosmos, including galaxies and clusters. The IGM acts as a bridge between galaxies, facilitating the flow of matter, energy, and radiation throughout space. It not only fills the space between galaxies but plays a part in the dynamic processes that occur on both the smallest and largest scales of the universe. Yet, despite its critical role, much of the IGM remains hidden, as its tenuous nature makes it difficult to detect. This enigma has led to one of the greatest challenges in modern astrophysics: understanding how to study and measure this diffuse and faint gas. One of the ways astronomers try to study the IGM is by observing the radiation from distant quasars. A quasar is an extremely energetic and compact object at the center of a distant galaxy, often powered by a supermassive black hole. As light from a quasar travels across vast distances to reach Earth, it passes through the IGM, and some of this light is absorbed or scattered by the gas in the medium. This interaction leaves a unique imprint on the light, which can be analyzed to reveal information about the composition, temperature, and density of the IGM. By examining these quasar spectra, scientists can piece together a more detailed picture of the IGM's properties and distribution across the universe. Moreover, the study of the cosmic microwave background (CMB) radiation has also provided crucial insights into the IGM and its role in the early universe. The CMB is the faint afterglow of the Big Bang, a remnant radiation that fills the entire universe. The IGM, as it existed in the early universe, interacted with this radiation, and studying these interactions has allowed scientists to gain insights into the early conditions of the universe. The CMB is like a snapshot of the universe just 380,000 years after the Big Bang, when the IGM was much denser and hotter than it is today. By analyzing the subtle patterns in the CMB, researchers can gain valuable clues about how the IGM contributed to the early formation of cosmic structures. The IGM's complex behavior is closely tied to its interactions with various forms of radiation. For example, ultraviolet (UV) radiation from the first stars and galaxies in the early universe had a profound impact on the IGM. This radiation helped to ionize the hydrogen in the IGM, turning it into a plasma of charged particles. This process, known as reionization, occurred when the universe was about 1 billion years old and marked the transition from an opaque universe to one that allowed light to travel freely. The study of reionization is vital for understanding the evolution of the IGM and the formation of the first galaxies. It also holds important clues about the nature of the first sources of light in the universe, such as the first stars and black holes. In addition to the observational techniques mentioned above, advancements in technology are helping scientists explore the IGM in increasingly precise ways. For instance, next-generation telescopes and space observatories are expected to enhance our ability to detect faint signals from the IGM. These instruments will provide more detailed images and spectra of the IGM, and allows scientists to probe its properties with unprecedented accuracy. The James Webb Space Telescope, JWST, for example, will play a crucial role in studying the distant universe, including the IGM. Its ability to observe infrared light will help scientists detect the faint signatures of the IGM and study the processes of galaxy formation and evolution in greater detail. Another breakthrough in our understanding of the IGM could come from the study of gravitational waves. These ripples in spacetime, caused by the acceleration of massive objects like black holes and neutron stars, could interact with the IGM, leaving behind subtle traces that can be detected by future gravitational wave observatories. By studying how gravitational waves interact with the IGM, scientists could gain new insights into the properties of this elusive gas and its role in the cosmos. This is still an emerging field, but the potential for new discoveries is immense. One fascinating aspect of the IGM is how it interacts with various cosmic phenomena. In galaxy clusters, the IGM can be seen as a vast and dynamic medium that participates in the ongoing evolution of these massive structures. When galaxies collide or pass through the IGM, they can trigger shock waves that heat up the gas and cause it to emit X-rays. This process, known as shock heating, is a key component in the life cycle of galaxy clusters. As the gas is heated to millions of degrees, it emits X-rays, which can be detected by telescopes like the Chandra X-ray Observatory. These X-rays provide valuable information about the distribution and temperature of the IGM within galaxy clusters, allowing scientists to study how these clusters grow and evolve over time. Another important aspect of the IGM's interactions with galaxy clusters is the phenomenon known as active galactic nuclei, AGN. These are supermassive black holes at the centers of galaxies that are actively accreting matter and emitting vast amounts of energy. The energy emitted by AGNs can have a significant impact on the surrounding IGM. The intense radiation from AGNs can heat the gas in the IGM, causing it to expand and change its properties. This process can influence the growth of galaxy clusters and the evolution of the IGM itself. Studying the relationship between AGNs and the IGM is crucial for understanding the complex interplay between galaxies, black holes, and the surrounding gas. Beyond galaxy clusters, the IGM also plays a key role in the large-scale structure of the universe. As the universe expands, the gas in the IGM is stretched out, and its properties change accordingly. Understanding how the IGM evolves over time is critical for studying the universe's history and predicting its future. The IGM is thought to be responsible for a variety of phenomena, such as the formation of cosmic voids, where matter is less dense. These voids are not truly empty but are filled with diffuse gas, and they represent a critical aspect of the universe's overall structure. By studying these voids and the IGM's role within them, scientists can learn more about the forces that shape the universe on the largest scales. The IGM is also a key player in the ongoing research into the nature of dark matter and dark energy. These mysterious substances make up the majority of the universe's mass and energy, but their properties remain largely unknown. One of the most exciting possibilities is that the IGM may be a key to unlocking the mysteries of these elusive substances. Some theories suggest that dark matter could interact with the gas in the IGM, affecting its properties and behavior. Understanding these interactions could help scientists develop better models of dark matter and dark energy, leading to breakthroughs in our understanding of the universe's most fundamental forces. While the IGM may seem like an obscure and distant concept, its role in shaping the universe is undeniable. This hidden matter, lurking between galaxies, is one of the most essential components of the cosmos. From influencing galaxy formation to shaping the large-scale structure of the universe, the IGM is a driving force behind the evolution of everything we observe. Its study is not just about understanding gas or plasma, it is about unlocking the secrets of the universe itself. As technology advances and our observational capabilities improve, the IGM will continue to reveal its secrets. From the birth of the first stars to the ongoing evolution of galaxy clusters, the IGM is a critical player in the universe's story. Every discovery about this elusive gas brings us closer to understanding the true nature of the cosmos and our place within it. It may take decades, even centuries, for us to fully comprehend the IGM's mysteries, But with each new breakthrough, we take another step toward unraveling the deepest secrets of the universe. As we venture deeper into the mysteries of the intergalactic medium, IGM, it becomes increasingly clear that this enigmatic substance holds the key to understanding the universe on both a micro and macro scale. The more we uncover about the IGM, the more we realize its profound impact on the structure and evolution of the universe. It's the invisible web that connects galaxies, stars, and other cosmic phenomena, forming the backbone of the cosmic landscape. Yet, much of this web remains undetected, hidden in the vast expanses between the galaxies, and its properties are still being unraveled by scientists. One of the most exciting aspects of studying the IGM is its connection to the large-scale structure of the universe. The universe is not a uniform, homogeneous expanse but is instead made up of vast regions of dense matter, separated by enormous voids filled with much less material. These regions of density and emptiness, known as the cosmic web, are shaped by the interactions of galaxies, dark matter, and the IGM. Galaxies tend to form at the intersections of these filaments, and the IGM plays a crucial role in this process by acting as the medium through which matter and energy flow. The IGM's interaction with dark matter and dark energy also holds great promise for advancing our understanding of these elusive forces. Dark matter, which makes up about 27% of the universe's mass, is thought to interact gravitationally with normal matter but does not emit, absorb, or reflect light, making it invisible to traditional observational methods. Dark energy, on the other hand, is believed to be responsible for the accelerated expansion of the universe, and it constitutes about 68% of the universe's energy content. While dark matter and dark energy have largely remained a mystery, the study of the IGM might offer clues to their behavior and interactions. Some astrophysicists speculate that dark matter could interact with the IGM in subtle ways, possibly through weak forces that don't produce detectable light or radiation but could affect the behavior of the gas. For example, dark matter could influence the distribution and movement of gas within galaxy clusters, potentially altering their structure and evolution. If we could detect these interactions, it could provide valuable insights into the nature of dark matter and its role in the universe's expansion. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, could have an indirect connection to the IGM. The stretching of space-time caused by dark energy could influence the expansion and cooling of the gas in the IGM. As the universe grows larger, the gas in the IGM becomes more diffuse, and its temperature decreases. Understanding how dark energy affects the IGM could offer a new perspective on the relationship between these two cosmological forces and help scientists develop a more comprehensive model of the universe's evolution. Another fascinating aspect of the IGM is its role in galaxy formation and evolution. The gas between galaxies plays a crucial role in the accretion of matter that forms new stars and galaxies. As gas from the IGM flows into the gravitational wells of galaxies and clusters, it can be compressed and heated to the point where it can form new stars and even black holes. The process of star formation is intricately linked to the properties of the IGM, particularly its density and temperature. In regions of the IGM where the gas is dense and cool, new stars are more likely to form. In contrast, in hotter and more diffuse regions, the gas may remain in a state of ionized plasma, unable to condense into new stars. The connection between the IGM and galaxy formation is also evident in the study of galaxy clusters. These massive structures, which are made up of hundreds or even thousands of galaxies, are surrounded by a dense IGM known as the intracluster medium, ICM. The ICM is composed of hot, ionized gas that emits X-rays, and its study has provided valuable insights into the dynamics of galaxy clusters. As galaxies move through the ICM, they experience a range of phenomena, including ram pressure stripping, which can remove gas from the galaxies, and shock heating, which can raise the temperature of the gas to millions of degrees. These interactions between galaxies and the ICM are essential for understanding the evolution of galaxy clusters and the role of the IGM in shaping the growth of large-scale cosmic structures. The study of the IGM is not limited to its interactions with galaxies and clusters. It also has implications for our understanding of the early universe. The IgM, in its primordial state, was much denser and hotter than it is today, and its behavior during the first few 100 million years after the Big Bang is a critical aspect of the universe's evolution. The period known as the cosmic dawn marks the time when the first stars and galaxies began to form, and the IgM underwent a dramatic transformation. The ultraviolet radiation from these early stars ionized the hydrogen in the IgM, causing it to transition from a neutral state to a fully ionized plasma. This process, known as reionization, is thought to have occurred between 400 million and 1 billion years after the Big Bang and is one of the key events in the history of the universe. The study of reionization and the role of the IgM during this time is a major focus of modern cosmology. By examining the properties of distant quasars, which emit light that travels through the IgM, astronomers can gain insights into the state of the gas during this critical period. Additionally, the cosmic microwave background (CMB) radiation provides a snapshot of the universe from just 380,000 years after the Big Bang, when the IgM was still in its primordial state. By studying the patterns in the CMB, scientists can learn about the density, temperature, and composition of the IgM at this early time, helping to piece together the puzzle of the universe's infancy. Understanding the IgM is also important for future space exploration. As our telescopes and observatories become more advanced, we will be able to study the IgM in greater detail, unlocking new insights into its properties and behavior. The next generation of space telescopes, such as the James Webb Space Telescope, JWST, will be able to study distant galaxies and their surrounding IgM in unprecedented detail. These observations will allow scientists to investigate how the IgM has evolved over time, how it influences galaxy formation, and how it interacts with other cosmic phenomena, such as dark matter and dark energy. Moreover, the IgM could provide a valuable resource for future space missions. As humanity looks toward the stars and the possibility of interstellar travel, understanding the IgM could help us better navigate the vast distances between galaxies. The gas in the IgM is not just an obstacle, it is also a potential source of knowledge about the larger cosmic processes at play. By studying how the IgM behaves, scientists can develop better models of space travel and explore ways to use the medium to our advantage in the future. Despite its importance, the IgM remains one of the least understood components of the universe. Its diffuse nature, low density, and faint emission make it challenging to study, but its role in shaping the universe is undeniable. As our understanding of the IgM continues to evolve, we are bound to uncover new and exciting insights into the fundamental workings of the cosmos. This hidden matter, which fills the vast spaces between galaxies, is not just an abstract concept, it is the very fabric of the universe itself. With each new discovery, we come closer to understanding the true nature of the cosmos and the forces that govern its evolution. The IgM, though invisible and elusive, is the thread that weaves together the cosmic tapestry. From the birth of galaxies to the ongoing evolution of the universe, it is a silent force that shapes the very fabric of the cosmos. As we continue to explore this hidden medium, we are bound to uncover more secrets that will challenge our understanding of the universe and our place within it. The IgM may be invisible, but its influence is vast, and the more we learn about it, the clearer the picture of the universe becomes. As we continue our journey through the mysteries of the intergalactic medium, IgM, we begin to realize that this elusive substance is far more than just an empty void between galaxies. It is an active and dynamic environment, constantly interacting with the universe's largest structures and influencing the processes that govern the evolution of galaxies, stars, and even black holes. The IgM is, in many ways, the unsung hero of cosmic evolution. Though it is invisible to the naked eye, its presence is felt everywhere, and understanding it is crucial to understanding the cosmos as a whole. One area where the IgM's role is especially critical is in the formation of galaxy clusters. These vast collections of galaxies, bound together by gravity, are some of the largest structures in the universe. However, galaxy clusters do not exist in isolation. They are surrounded by a dense IgM, or more specifically, the intracluster medium, ICM. This hot, ionized gas permeates galaxy clusters and plays an essential role in the dynamics of these massive systems. The ICM is made up of gas that is millions of degrees hot, and its temperature is primarily governed by the complex interplay of gravity, shock waves, and the energy emitted by active galaxies and their central supermassive black holes. The ICM is not just a passive medium, it actively affects the galaxies within a cluster. For example, galaxies that move through the ICM can lose their gas through a process called ram pressure stripping. This phenomenon occurs when the hot gas in the ICM exerts pressure on the gas in a galaxy, essentially stripping it away. Over time, this can affect a galaxy's ability to form new stars and influence its overall evolution. In addition to ram pressure stripping, another key process within galaxy clusters involves the cooling of the ICM. As the gas within a cluster cools, it can condense and form clumps of matter, which may eventually collapse to form new stars. However, this cooling process is complicated by the fact that the gas in the ICM is constantly being heated by various processes, such as the movement of galaxies within the cluster, shocks from supernovae, and the radiation emitted by active black holes. These processes create a delicate balance between heating and cooling in the ICM, and understanding this balance is crucial for understanding the evolution of galaxy clusters and the role of the IGM in shaping the universe. The role of the IGM in the formation of galaxy clusters also has important implications for the study of dark matter. As we've seen, galaxy clusters are held together by the gravitational pull of dark matter, which is invisible and detectable only through its gravitational effects. The IGM, particularly the ICM, interacts with dark matter in subtle ways. For instance, the distribution of the ICM can be influenced by the presence of dark matter, and the study of the ICM can provide indirect clues about the distribution and properties of dark matter in galaxy clusters. By mapping the ICM, scientists can create more accurate models of dark matter's distribution and improve our understanding of this mysterious substance. Beyond galaxy clusters, the IGM also plays a crucial role in the overall structure of the universe. The cosmic web, a vast network of filaments and voids that stretches across the universe, is shaped by the interplay between galaxies, dark matter, and the IGM. These cosmic filaments are made up of dense concentrations of matter, including galaxies, stars, and gas, and they are interconnected by the vast, largely empty voids that exist between them. The IGM forms the backdrop to this cosmic web, filling the spaces between galaxies and clusters, and its properties are intricately tied to the overall structure of the universe. One of the key features of the IGM is its role in the process of cosmic reionization. As we discussed earlier, the IGM was originally composed of neutral hydrogen gas that was opaque to light, creating a fog that made it difficult for light to travel freely across the universe. However, during the epoch of reionization, which occurred roughly 400 million to 1 billion years after the Big Bang, the first stars and galaxies began to form, and their ultraviolet radiation began to ionize the hydrogen gas in the IGM. This ionization process allowed light to travel more freely, and it marked the end of the cosmic dark ages and the beginning of the universe's transparent state. The study of reionization is crucial because it provides a snapshot of the universe during one of its most formative periods. By observing distant quasars and galaxies, astronomers can study the state of the IGM during this time and gain insights into the processes that led to the formation of the first stars and galaxies. Reionization also had a profound impact on the large-scale structure of the universe, as the ionization of the IGM affected the way matter was distributed across the cosmos. By studying the IGM's role in reionization, scientists can better understand how the universe evolved from its early, dense state to the vast, complex structure that we see today. Another fascinating aspect of the IGM is its relationship with black holes. Supermassive black holes, which reside at the centers of most galaxies, are among the most powerful and enigmatic objects in the universe. These black holes can exert immense gravitational forces on their surroundings, and they can influence the IGM in a variety of ways. One of the most striking examples of this is the phenomenon known as feedback, which occurs when the energy and radiation emitted by a black hole affect the gas in its vicinity. In many cases, the radiation from a supermassive black hole can heat up the surrounding IGM, preventing it from cooling and condensing into new stars. This process, known as preventive feedback, can have a profound effect on the growth and evolution of galaxies. In some cases, black holes can even expel gas from their host galaxies in powerful jets, creating large-scale outflows of gas that can impact the surrounding IGM. These interactions between black holes and the IGM are crucial for understanding the regulation of star formation in galaxies and the overall dynamics of the universe. The study of black hole feedback and its influence on the IGM is an exciting area of research, as it could shed light on the role that black holes play in the formation and evolution of galaxies. By observing the way that black holes interact with their surrounding gas, scientists can gain insights into the processes that govern galaxy growth and the formation of cosmic structures. In this sense, the IGM serves as both a medium through which galaxies and black holes interact and a crucial player in the larger cosmic drama of the universe's evolution. As our understanding of the IGM continues to grow, new questions and mysteries arise. One of the most intriguing aspects of the IGM is its potential connection to the missing baryons in the universe. Baryons are the particles that make up ordinary matter, such as protons and neutrons, and they account for only about 5% of the universe's total energy content. However, the amount of baryons observed in galaxies and galaxy clusters falls short of what would be expected based on current models of the universe. Where, then, are the missing baryons? One possible answer lies in the IGM. Some scientists speculate that a significant portion of the missing baryons could be hidden in the diffuse gas of the IGM, where they remain undetectable due to the faint nature of the gas and the difficulty of observing it across vast distances. By studying the IGM in greater detail, scientists hope to uncover the location of these missing baryons and refine our understanding of the distribution of ordinary matter in the universe. This question of missing baryons highlights the importance of continued research into the IGM. As technology improves and new telescopes and observatories are launched, we will have more tools at our disposal to study the IGM and its properties. Instruments such as the James Webb Space Telescope, JWST, and the upcoming next-generation radio telescopes will allow us to observe the universe in new and unprecedented ways, providing fresh insights into the IGM's role in the evolution of galaxies, stars, and the universe itself. In conclusion, the intergalactic medium may be invisible and often overlooked, but it is one of the most critical components of the universe. From shaping the large-scale structure of the cosmos to influencing galaxy formation and the behavior of dark matter, the IGM is a silent architect of the universe's evolution. As we continue to explore its mysteries, we uncover new and exciting insights into the nature of the cosmos and our place within it. The IGM is not just a passive backdrop to the universe's grand narrative, it is a vital, active player in the cosmic drama that unfolds across the vast expanse of space. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.